So this would be the 2009 paper, right? 2009 kinetics and equilibrium, rates of reaction. So let's have a go at this. State two factors which affect the rates of reaction. Let's go quickly. Give us one. Somebody give me one.
Surface area.
Surface area. What else?
Surface area.
Lovely. Surface area. What else?
And concentration.
Concentration in aqueous solutions.
Temperature.
Lovely. Temperature. What else? If you could use pressure in gaseous solutions, in gaseous mixtures, what else could we use? We could use light in decompositions. Anything else? Those would be it, right?
Sir, light.
Yes. Light can affect the rate of reaction. It's dependent on different things. And what we should know at this level is
Sir,
that
catalyst.
okay, H2O2. And then we have catalysts. So catalysts, okay, light can affect the rate of reaction, right? Especially when we look at the decomposition reactions of hydrogen peroxide, light is the main thing. When you go into the labs and you see those dark bottles or brown colored bottles, right, with reagents in them, there's a reason why we make them dark, because light can decompose them and increase the rate of decomposition. So some compounds, some substances, we keep them in those dark bottles, right? Especially organic substances, they
Like
come in dark
hydrogen
bottles.
peroxide.
Lovely. If you look at hydrogen peroxide, the bottles tend to always be brown or some dark color, brown, black, or something. All right. Table one.
Sir, like the silver.
Silver.
Is it silver nitrate?
Silver nitrate. I believe that I've seen silver nitrate in dark containers. Mhm. So anything you see in a dark container, there's a reason why it is placed in that. All right. So the data in table one were data. Okay, yeah, were obtained for the decomposition of nitrogen dioxide, right, at 673 Kelvin. So here we have this decomposition. Now complete the table, writing the missing values for that. How will we complete the table? How would you guys go about completing this table?
Just put 1 divided by the moles of NO2.
All
So
right.
for the second one, it would be 1 divided by 0.00787.
And that should give us what, 127, right? Right? And then this one would give us now what, 208. And that is our table. 2 marks, 3 marks, all done. Okay, because if this is the concentration of our nitrogen dioxide and this is 1 over the concentration of nitrogen dioxide, then 1 over everything and you should be fine. Lovely. So let's have a move on now. This is a very old paper, by the way. So I saw this, right? And I just put in the points for this so far. When I saw the paper, I was like, I can't just sketch graphs, so I might as well put in the points. So I put in the points here. Right? So you guys, I don't think going through graphs would make sense, right? Because at this level, we should be proficient with graphs, right? So you should be able to create your graphs like that, right? With your line of best fit now, you're going to be passing through as many suitable points as possible, right? And we're gonna end up with a line that looks kind of like that. You're gonna have a few outliers, but that's how a line of best fit works, right? So we're gonna have a graph that looks like that when you plot the points. All right. Obviously, this line is not straight. We need a rule on actual paper. But yeah, you can have something looking like that. All right. Okay, so I don't hear any questions or concerns with this. You just plot your point, then draw the graph. All right. Now, from your graph, determine the order of reaction with respect to nitrogen dioxide and give us a reason. Determine the order. This is interesting because I have a feeling that we may use a certain rate law. All right, go ahead. Any ideas? Go ahead.
So would it be first order because it's constant?
Not necessarily. Would it be first order? Let's have a look at this reaction. Hold on. Let's check if it would be first order. So do we think it would be first order? I don't think this information up here can help you at all. That not help you. Alright, so we have to really look at, notice that rate is not given in the table as well. So you can't look on the rate and say, oh, the rate doubles or quadruples, not help you. Right? Technically you could find the rate, you could calculate the rate and see how it works, because rate is divided by the change in concentration over time. Right? But alright, you could do that. But what's happening here? Okay, why would it be first order? You're saying because the rate is not constant here, right? And notice that rate is not on the graph, so you can't use the graph to figure out the rate because rate is not on the graph. So you can say the rate is in. Okay, let's see what's happening here. Any other ideas? Because somebody said rate, we'll figure that out when we reach there. If it is really the rate increasing.
So I think it's first order too.
Okay, we think it's first order. All right. So what is a first order reaction graph is going to look like? What is that going to look like?
Well, okay, so the zero order one is like the straight line across, and the first order one is basically this one going
Alright.
straight up, and the second one is going straight up but it's curved. So,
Alright,
and
so
this one looks the closest to first.
I'm so sorry, this is going all over the place. Alright, let's draw. No, I don't want to draw the graphs down here. Let's draw the graphs right here. Alright, right here should be fine. Alright, so we're saying that zero order. What would zero order be?
Zero order would be a straight line.
In this case, no, right? We're looking at concentration time graphs, right? Not a concentration, well, not a rate concentration graph. So that will not be zero order. What will zero order reactions look in concentration time graphs? There's a difference. Okay, let's put zero order here. Let's just put as zero order here, right? With concentration time. So concentration and time. And here we'll put the rate and the concentration. And let's draw all of these graphs and get them done right now. Right? So let's look at these now. With zero order, concentration time graphs will look like this. Right? With the rate graphs, it will look like this. First order, right? Our concentration time graph for first order will look like this, right? And the rate concentration graph will look like that. The graphs need to be remembered, guys. So second order now. If with the second order, we're gonna have something looking like this, right? and we're gonna have something looking like this for the rate versus concentration. All right, so those are our graphs, right? So which graph does this thing look like? Because what you guys are rightfully saying is that this would be a first order reaction graph only if this was rate versus concentration, which it is not. So what order of reaction is it? Are you guys understanding what I'm saying? It's not rate versus concentration.
Sir, the top graphs are. So what are on the axis is for
Oh,
the
the
top
axis.
graph?
Oh, sorry about that. Oh, it's concentration versus time. Therefore, concentration would be on the y, and time would be on the x. Because that's how we, right? It's a concentration versus time, right? And then rate versus concentration would be rate on the y-axis, concentration on the x-axis. So, and the variable that comes first goes on the y, variable that comes second goes on the x, right? So we have that there. I think what is happening here is no longer taught on the syllabus. I think that is it. Let me look at the syllabus real quick. Right, this is my assumption that it is no longer taught on the syllabus. Let's look at the rate of reactions. So the experiments deduce the experimental. Is it taught? This is interesting. Any other assumption as to what the graph would be? I did this in my rates video, but I don't think it's on the syllabus. Alright, so let's have a look at this. Right? This is an inverse concentration versus time graph. Right? And that is obtained from an integrated rate law. Right? So using integration, a little bit of maths. Right? If we integrate the rate law, we should be able to get a graph like this, right? So our general rate law for first order, second order, and zero order reactions, we should know what those are. We should have a general understanding of what those are, right? So in this case now, if we use the integrated rate, this would be the integrated rate law for a second order reaction, right? So what is the integrated rate law? Let me write that. I'm not sure if it's still taught, but I was taught it when I was doing unit 1, so I would just do it here. If we have inverse concentration versus time, right, that is the graph for an integrated rate law showing the second order reaction, right? And the integrated rate law will be the 1 over the concentration of the thing, right, would be equal 1 over the initial concentration. Yet again, I'm not sure if you guys did this, right, plus KT, K being the rate constant, K, and T being T being time, right? So with that now, if we linearize the formula, y equal mx plus b. If we linearize it now, we should be able to get the entire thing. Why am I linearizing it? I'm linearizing it because it gives you the understanding of what is present there, right? So on the y-axis, right, we will just have the concentration, right? So if we linearize it, the y would be the inverse concentration, and that is what is on our y-axis here. Hopefully we can see that, right? And then our gradient would be k, right? And then our x will be time, and then our b would just be initial concentration, really. one over the initial concentration, which really doesn't matter in this case, right? So based on the fact that it's an inverse concentration graph versus time, this is the integrated rate law for the second order reaction. So this reaction should be second order, right? And yeah, so the order is second order. So it's ORDER, order, right? And the reason would be because of this, right? If we have a graph, right, that is inverse concentration versus time, and if that graph gives us a directly straight line, right? If it gives us a best fit, right, then that would be second order, right, based off of the equation of the line for the second order rate law. Right, so it is a second order reaction. Yet again, I'm not sure if this is still done on the syllabus. Right, and if we state the rate law for the reaction, right, the overall rate law, the initial rate law that we have, right, the rate law is simply the rate for second order reactions. Wait, question, what is rate law for second order reactions? You guys should be able to give me that really quick. What's the rate law? What's the rate law? For second order reactions, what is the rate law? Let me ask that.
The rate equation.
Rate law, rate equation, same thing. Go ahead. What would be it? All right, so the rate law itself, right, will be the rate constant K times the concentration of nitrogen dioxide. Why that look like hydrogen? It's nitrogen dioxide squared by second order. All right. Use the slope of the graph, determine the value of the units of the rate constant, value and units of the rate constant K for the reaction, right? All you're going to be doing is calculating the gradient, right? Which is y2 minus y1 over x2 minus x1, right? So you're gonna just calculate the gradient of your curve, right? And that's that you're going to get your entire value for K, right? And your rate constant K, the units of K for second order reactions would be what? It would be mole squared per dm, right, to what? dm to what? You have dm cubed squared. What would that be? So the 6, you guys said?
Yeah.
All right. So remember, dm cube times dm cube. All you're going to be doing here is what? The exponents. What you do with the exponents? Just remind me of what you do with the exponents, please. Alright, so what we're gonna basically be doing is adding the exponents, right? With the second law of indices, just math, right? That would be the unit, and then what you're gonna be doing is putting your answer for your gradient here, right? I can't actually do graphs here. That would be a gradient. So once you get the gradient of the curve, and then you drop your unit at the end of it, and that would be your answer. Alright, so that is that question for 2009. And yes, as we go back throughout the years, they should become more difficult. Alright, so here now, several experimental methods, including titration, can be used to determine the reaction rates. Suggest 2 other methods which can be used to determine reaction rates. So other than titration, which will rule out potentiometry and all other types of metry, right? Because some persons would put, oh, titration is only titration. That's not true, right? So without using titration, how can we actually determine the reaction rates? There are two simple ones that we got from CSEP. Ladies and gentlemen, how can we determine the rate of reaction without using titration? So we have a
Sir,
gas.
can we use the gas syringe?
Lovely, the gas syringe. We can use the gas syringe, or we could use the, starts with the I, two words. The first word starts with I, and then the second word starts with a C. We take something and we turn it upside down. The inverted cylinder. You can use an inverted cylinder as well. Alright. Okay, to measure the rate of reaction. Alright, so they didn't say what specific parameters, but that would be two other methods that they're suggesting, right? So they just ask what other two methods, right? So you don't have to be parameter specific, but two methods them ask for, two methods that, alright? Outline two experimental steps in determining the rate of reaction of an esterification reaction using titration. Two experimental steps for determining the rate of reaction of esterification reaction. It doesn't have to be in order, they just ask for two steps. So it would be two steps in your titration. Ladies and gentlemen, are we understanding the question? Daniel, do you understand the question? Denisha, do you understand the question? Rian and Kadeem, do you understand the question? Shanique and Zach, do you understand the question?
Excuse me, sir.
Go ahead.
So I went away from my device for a bit, sir. Sir, what was the answer for the graph question?
Okay, we're going to get back to that, but let us just complete this here because this is the end of the 2009's rates of reactions, right? So let's just complete this and we'll go back up. So we're just outlining two experimental steps in the determination of the rate, right, of an esterification reaction using titration. Two steps towards. Anybody can give me one step? What would you do in a titration?
So you have a yes, sir. So you have a you have a solution with a known concentration, and you have a tire, which is titer, which is the solution with the unknown concentration that you want to find the concentration for. So the titer will be placed in the burette, and the solution you'd measure a specific amount and place it in the conical flask.
Hold on. You said that your titer would be the solution that you don't know the concentration of? let's use the word
Sir,
analyze.
what?
Let's use the word analyze. The thing is now, titrator is generally the same thing, right? But just in case, we can use analyze reciprocating that, right? If we do not know the concentration of a substance, we put that in the conical flask. I don't know if you misspoke, but you said burette. You don't put the unknown solution in burette. Put the known solution in the burette. Isn't that what you do? What do you do?
Oh, yes, sir. Yes, sir.
Alright, so we know what is in the burette. And then we add the 25 or whatever amount of TM cubes, right, or CM cubes of the solution that we don't know into the conical flask. But what we're trying to do now, we're not really trying to find the concentration of ester or anything like that. What we're trying to find is reaction rate. So first of all, in order to figure out our endpoint in any type of stoichiometry, right? And from CSEC, we'll have known that the esterification involves the addition of an acid and an alcohol. I would use one of my important steps would be adding a suitable indicator to my analyte. That would be one of my crucial steps. A suitable indicator. And by the fact that esterification is formed through a weak acid or organic acids have a low pH, right? Therefore, a suitable indicator would be thymol blue or phenolphthalein. So I will add a suitable indicator, for example, phenolphthalein, to my analyte. That would be one key experimental step that I will have to do for the determination of my reaction rate. Because what I'm going to do is measure how fast the reaction reaches its endpoint, and in order to know the endpoint, I must have my indicator. Right? And that's if it is acid-base stoichiometry. Right? Why am I using acid-base stoichiometry? Is because our brains naturally go to acid-base stoichiometry when we're doing unit 1. Right? So using acid-base stoichiometry, addition of a suitable indicator would be key. Another important experimental step that I would actually do would be varying the concentrations now, right, of my alcohol or my acid, so I can see how the reaction rate changes, right? That is really just determining the order of reaction, right? But it can also help in determining our reaction rate. So we're gonna actually figure out, so the first experimental step, right, we add our indicator to know our endpoint, right? Our second step could literally be conditioning our instruments, right? Our second step could be I'm not sure, using a stopwatch, right? We could use different types of experimental techniques, but what are two key steps in determining the rate of reaction using stoichiometry? We need to have two of those steps down, right? So one crucial one would be the addition of our indicator, right? And another crucial one would be timing how fast it reaches the endpoint. So it's just logics, right? It's just thinking about what you're doing. And if you're in a lab setting, what would you do to find the rate of reaction? That's what we're doing, all right? And that would be the end of this section here. Are there any major questions that we'll have? That would be the end of our question, all right?